A building is an environmental separator. It separates the inside from the outside, and if you don't get it or get that concept, nothing else really matters. It means you want to keep the outside out and the inside in. And many people say, well, I want to bring the outside in. Well, yeah, but you only want that to happen when the outside is at the condition that you like. And so many parts of the year and in many places in the world, you don't want the outside condition to be in the inside. So first and foremost, it's an environmental separator. In order to do that, you actually have to build an enclosure. And the saying is before you can control air, you must first enclose air. So this enclosure needs to keep the air outside and the air inside. It has to keep the rain outside. And if any water or moisture gets into the enclosure, it needs to allow that to get both to the outside and to the inside. So the rules for environmental separation are pretty straightforward. You need a water management system for rain and groundwater. You need an air barrier to control the air. And you may or may not need a vapor barrier or vapor retarder, depending on where you are, to control or manage the moisture. Well, the United States is an air conditioning dominated nation. It doesn't seem that way when you're experiencing winter, but the United States is unique in that regard. It's the only industrialized nation dominated by air conditioning. That means that the inside tends to be cold and the outside tends to be hot. Duh. Well, heat flow and moisture flow are always from warm to cold. So you want your vapor control layer on the outside in an air conditioning dominated climate. So in Texas and Oklahoma, if you're going to have a vapor retarder or a vapor barrier at all, it should be on the outside. You should never have one on the inside. So you should never put vinyl wallpaper on the inside of your building. You should never use polyethylene on the inside of your building as a vapor barrier or an air barrier. You should never use a craft-faced fiberglass bat. It should be an unfaced bat. You should never use aluminum foil on fiberglass cavity insulation. You should never use aluminum foil-backed gypsum board. You should never use oil-based or epoxy paints. The United States is a really interesting place as you go from Miami to Memphis, from Memphis to Muncie, from Muncie to Minneapolis, and from Minneapolis to the Mojave, and from Mojave to Monterey. And each of those places has a different temperature and humidity regime. Also, each of those places has a very, very different rainfall. You go from lots and lots of rain in Miami to almost no rain at all in the Mojave. Well, based on temperature, humidity, and rain, you're going to have a different environmental separation approach, that separates the outside from the inside. So geography is pretty darn important. You actually have to know where you are before you decide how to build the enclosure. That's also going to determine how you heat or cool, humidify, dehumidify, filter the air. Because the air inside came from where? Outside. So you have to decide, when you bring the outside air to the inside, what are you going to do with it, and how are you going to do that? Well, the ideal wall is a wall that keeps the rain out, keeps the outside air out, the inside air in, and lets the water vapor out either to the outside or to the inside or to both sides. And depending on where you are is going to determine what that wall configuration looks like. In the south, you want your vapor control on the outside. In the north, and the real far north, remember Alaska is part of the United States, you'd want your vapor control on the inside. And so this map and this geography is a huge factor in determining what the optimal enclosure is and what the optimal mechanical system is within that enclosure. I think what we've learned over the last 50 years is that we want our control surfaces on the outside of the structure, and that those control surfaces should be protected from water, heat, and ultraviolet light with insulating sheathing. So for example, if you wanted to build a building enclosure that would last 500 years, you'd build a structure, for example, out of wood or concrete or steel, and put your air barrier, vapor barrier membrane layer on the outside of that structure, and then put all of your insulation to the outboard of that with a cladding system. That may not be the most practical and cost-effective way to build a building, but in terms of what we're doing today, it's pretty clear that we can economically build a wood frame wall with advanced framing, have an exterior sheathing with a building paper or a house wrap, and then outboard of that have 1 or 2 inches of insulating sheathing. So I think the wall of the future, and when I mean the future, the near term, the next decade, will be walls with insulating sheathings almost throughout the United States. And the thickness of the insulating sheathings and the characteristics that those sheathings have in terms of water control and permeability will be based on where you are. So, the general configuration will be similar between Key West and Bangor, Maine, but the actual R value and permeability of the individual components will be very climate specific. Well, what we know through experience is that the heavier things are, the more expensive they are. I know that sounds incredibly simple, but it's true. The more something weighs, the more it costs. And so the affordable structure of the future is going to be a very lightweight structure. So buildings are getting lighter and lighter. You see that in commercial and institutional buildings. You see that in residential. What we want to do is take out as much as we can without compromising performance. So I call it Goldilocks. You can't take out too much. You can't take out too little. You got to take out just the amount. And so what we're finding is that there's probably between 30 and 40% too many framing members in the typical wood frame residential enclosure. What we need to do is take out the ones that we don't need. And as the ultimate irony, though, there's all kinds of things that we're not putting into the exterior enclosure as well. So as we take stuff out, we're actually going to have to put other stuff in that wasn't normally there. So for example, draft stopping that benefits us not just from an air control perspective, but fire control and other structural issues. I mean, the first thing that we got to do here is not kill anybody. So the house can't blow away and it can't burn down. Then we have to make sure that people don't get sick in it, and then we need to worry about energy. So energy is a big darn deal, but it's not as important as staying alive. And so the idea is, how do we achieve this energy efficiency and cost affordability without compromising fundamental safety? Well, what we've learned through, Euclid and Aristotle and the Greeks is that the most efficient way to enclose a space is to build a sphere, right? So the maximum volume is contained by a sphere. Well, the trouble is it's kind of hard to build round surfaces. Of course, architects haven't figured that out. They're always giving us these curved surfaces, but pretty much we're going to build with a square box or a cube is the most efficient way to enclose a space. So rather than having buildings that are spread out, we're going to have them more compact and more cubic. So we're going to have a larger volume, but we're minimizing surface area. So I expect that we're going to see taller walls, but less expansive roofs and foundations, and fewer interior penetrations and separations. What that means for us is that we're going to have to figure out how to keep the wind from blowing these things over, and we're going to have to make sure that they don't fall apart in an earthquake and that they don't burn, because the taller a wall is, the more complicated the fire control happens to be. The other trend is that you're going to find that, and we're finding now, is that roofs that are vented are pretty much wasted space. You've got all that material up there that's not useful. So we're going to be pushing the insulation levels to the skin of the building. So you're going to see the attic become a conditioned space. You're going to see conditioning pushed down into the basements and the crawl spaces and even into the garages. So the outermost skin is going to be where all of the temperature and thermal and structural control elements are going to be so that the entire interior volume of the outside that's contained by the skin becomes useful.